So, good morning. We are having our last class before mid semester, and that is why we will finish the topic of filters today. Filters means input output filters, and take up new topics after the mid semester. So today we will talk about adaptive filters little bit, that is those filters that we have. What sort of a problem have we seen before? We have seen that if we take a filter structure, we have mostly worked with FIR structure. We have seen that given the statistics of the data, how to calculate weights in that is the coefficients of the FIR filter such that you get minimum mean square error. This problem we have solved. Now in practice there are several reasons why in practice adaptive filters are very well used. So adaptive filters are filters where you don't, it's not that you are going to take a lot of effort and then calculate the noise statistics nicely and then you will calculate one set of weights and then freeze them. It's not going to, that usually doesn't work. So what works is that you have that filter structure and then you keep on changing the weights. I mean you keep on kind of sensing the noise statistics all the time, and depending on the kind of noise statistics that you see, you keep on changing the weights, right? So you have an element of adaptation in these filters. Okay, so we are going to, what we are going to see today is, let people sit down, then we'll continue. So so what we are going to see today is what are the basic ideas of adapting. Adaptation is a rather complex business. I mean, it's not, whenever you have an adaptive system, its behavior, to analyze its behavior is not trivial. It involves various things, quite complicated. But we will not go into all that. We will we'll do two things. Firstly, we will try to identify some basic rationales for adaptation. That is, if we want to change weights, what should be our basic guiding principles, and then we will see two major algorithms which are quite used and see how they satisfy those principles and try to ensure that they have good properties. Other than that, we are not going to do anything. You can have, I mean, whole volumes and hundreds of papers written on adaptive filters, but we are not going to do all that. We are going to look at it in one class. So we will basically look at two major algorithms. One is called steepest descent and the other is called LMS. There are various other versions of adaptive filters which we are not going to consider in this course. So to begin with, anywhere you have adaptation, it generally happens that you have something which is either unknown or time varying. So you have, when something is unknown, what you do is you start with some guess, and then you keep on improving your guess based on some criterion. So you adapt your guess, and hopefully if your adaptation rule is good enough, you will come fairly close to the real good guess, right? Which is maybe which is the true value. It sometimes happens that the situation changes. That is, suppose now you have one kind of noise statistics, after 2 seconds you have another kind of noise statistics. So it's not possible to have a constant set of optimal Wiener filter coefficients. because things are going to change, and you cannot pre-compute them. So in such a situation, you also need to have a scheme which will continuously track these changes in the data and will always produce coefficients which are going to be good, if not optimal. So they will, if things do not change, they will slowly approach optimal. If things change, they will at least track the change, right? This is the best that you can hope for. So in such situations, you need adaptive algorithms, and typical cases where these algorithms are used, these adaptive filters, are in, you know, echo cancellation. I mean, have you seen that? I mean, especially if you ever happen to talk in overseas calls, telephone calls, you can actually make out that there is a propagation delay, right? And sometimes there is, I mean, because of this propagation delay, sometimes there tends to be echoes because the transmitter and the receiver are not fully decoupled. So when the signal which comes, to some extent it also gets into the receiver, and then it is fed back to you, right? So you tend to get an echo. So it happens that most telecommunication equipment have what is known as echo cancellers. So they and these echoes depend on the kind of, you know, the kind of circuit which is downstream of the point where you put the echo canceller, and that can change because the telephone exchange configuration is very dynamic. It's a continuously switched set of systems, so you don't know what is the exact properties of the system which is downstream at any given point of time. So you need to adapt, right? Similarly, you can have things like, you know, channel equalization, that is where you try to correct for, in the received signal, you try to correct for attenuations and phase lags which have occurred in the channel, and channels can be dynamically changing. For example, a radio channel can change very much depending on, you know, weather and other things. So channel characteristics may change, right? So whenever you need to equalize something, you need to have it as adaptive. And then also for speech coding, because, you know, speech coding filters also need to be changed depending on who is speaking, various kinds of, you know, I mean, frequency spectrum, etc. Everything will change depending on the person who is speaking at any given point of time. So even you can have an adaptive coding scheme. So there are various kinds of, I mean, I just wanted to say that there are various kinds of applications where these adaptive filters are used. Basically, in any adaptive systems, and that includes an adaptive filter, the basic structure is like this. You know, you have a filter. This is the filter which you want to adapt, so that you get some good performance in the output. If you have, you know, in the case of signal processing, this is a filter. You could have an adaptive control. You could have so many other things. So now what happens is that this output, the properties of this output are evaluated. That is, this is some performance evaluation block. So you have to define some performance criterion, typically in terms of the outputs, so that you can evaluate whether this output is good enough or not, right? And this performance evaluation function generally gives some quantity which is used by the adaptation rule. So this adaptation rule is a rule which changes the coefficients in this filter such that you get such an output for which the performance criterion is minimized. So you should always try to minimize some performance criterion, and you continuously try to change your weights such that always this performance criterion when evaluated evaluates to be 0, as small as possible. So this is the structure of most adaptive systems. I mean, otherwise how do you adapt, right? So you have three major quantities. You have a filter structure, this one, in which you change the coefficients. So you have to define that. You have to define a performance criterion, maybe some noise square or whatever you define, and you need to have an adaptation rule. So whenever you want to define an adaptive system, these three quantities have to be defined. You have to define a filter structure, you have to define a performance criterion, and you have to define an adaptation rule. Then you have then if you put them together, you have an adaptive system, right? So now,
performance criteria and adaptive rules are fixed.
yes, yes. You can have various levels of adaptation, right? For that matter, control is also a kind of adaptation in the sense that you don't apply a constant signal. It is an adaptation at the signal level. So the signal changes, signal magnitude changes depending on the error. Then at a higher level of adaptation, you actually try to change the controller coefficients. That's what we call adaptation. Now if you want to change any one of these dynamically, then you are trying to change the adaptation rule. You are trying to change the adaptive system itself. Such systems are generally called learning systems. So learning systems is a higher level of adaptation, where you try to change the adaptation system itself, which changes the controller in turn, which changes the signal in turn, right? So you can have various levels of things, but this is what is generally understood as adaptation. So in our case, we have that well-known filter structure which you are very familiar with. So we are still trying to predict from samples of U by an FIR structure some signal Y. This is what we know. We have tried to see, and we have seen what are optimal estimates for this, etc., etc. So this is the filter structure we have defined that we are going to consider. What is our performance criterion? Performance criterion is this. So we have, these are the things that we are going to adapt such that this is minimized. So obviously the performance criteria depends on En, which depends on y hat n, which depends on Hn. So therefore the performance criteria depends on Hn. So if we change this, this will change. So our objective is to change these, adapt these, which are the coefficients of the filter, such that this quantity is minimized, right? This is our intention, and this we must be able to do all the time. Even if the signal properties D and R change with time, we should make corresponding changes in our estimate automatically, right? That is the problem. So we are familiar with this formula. This is standard, this Yn. If in place of y hat n you put this and then do E transpose, rather E transpose E, then you get this formula. This we have done in last class also. This is a well-known formula, right? This is simply y minus H transpose U whole transpose y minus H transpose U. If we just cross multiply, you will get this term. This is clear? No? So we have this filter structure and we have this performance criterion. Now the main thing is to design an adaptation law. So we have indicated what we want to change, and we have indicated our wish that we want to minimize this. This is our wish. Now we have to answer the crucial question as to how to satisfy our wish. So typical adaptive algorithms are, there are two guiding principles. You will find that 95%, probably 99% of all adaptive algorithms come in this form. That is, whatever you want to adapt, say in this case we want to adapt Hn, right? So the new weight Hn plus 1, you are continuously, as you are getting new data, you are adapting the weight. So for every data sample you are getting you are computing a new weight. So it always turns out that such an adaptation law results. This you will find in adaptive control. There are hundreds of adaptive control laws. Similarly, in all adaptive filter laws, almost all adaptive systems adaptation laws come in this form. So you have the new weight which you compute in terms. This is your old weight, and you want to update. So always you try to compute some form of an error, that is something that would have happened, which would be zero if the weights were really good, because if the weights were really good, then that error will be zero, and then there will be there will be no updating. So you see, if the weights are really good, you don't want to change it. You want to change it only when the weights are not good. So you will always compute whether the weights are really good in terms of some kind of an error. These, I mean, all algorithms vary in defining this error, defining this gain. So all variations come because of these two definitions. Otherwise, they are generally in this form. So you will define some error, and you will define, and then based on that error, you are going to change it using some gain. So these two remain to be determined. But this is the structure in which you always adapt your system. Now the question is, and there is also another very sound principle. That is, after all, you want to, what do you want to do? You want to minimize J, right? Your objective is to minimize that J function which you have defined. So if you want to minimize that, then in which direction you should change H? You should change it in the direction in which J is decreasing, is it not? You should change H, say J changes with H. So there is a rate of change of J with H. Now suppose whatever is the, so you should always change H in such a direction that J reduces. This is a I mean, sound principle, intuitively okay. So how do you find that direction? So it says that you calculate this one. Oh, there is a big manufacturing defect in these pens. So what is done is you calculate del J del H. So what is del J del H? Del J del H says that if you change H to H plus delta H, then J changes to J plus delta J. So you should always update in the direction of minus del J del H. This is a why?
Because its tendency is other side.
Yes, because if you change H to H plus delta J, H plus delta H, then J will change to J plus delta J. You want J to reduce, so you make it change towards minus delta J, right? So you always change. So this is most of the, I mean, a large number of adaptive algorithms are actually gradient algorithms, where the update is actually based on the gradient of the performance function. For example, all neural network training algorithms, most neural network training algorithms are gradient algorithms. That's also an adaptation. You are adapting weights to match something. It is exactly this problem. It is exactly the adaptive filtering problem, training of neural nets. So everywhere, so this is a standard rule that you update your weights in the negative of the gradient direction, right? So that your performance criterion is always decreasing. At every point it is decreasing, right? So here also, so we found, now let us calculate del J del H from where? From this formula. We know already J in terms of H. Here we already have J in terms of H. So we find del J del H from here. That's very easy to find. This term will give you a D, this term will give you a D, and this term will give you 2RH. Right? So you get minus 2D plus 2RH. So del J del H is minus 2D plus 2RH. So what is going to be your, now you have to do it, this is your adaptation gain and this is your minus del J del H. I mean, there is a factor of half which can be absorbed here. That factor of 2 is not a problem. You have to define this such that the factor of 2 is absorbed. Okay. So now, so this is now your adaptation rule, which ensures that at every point the gradient is decreasing, right? Now how do you characterize that? Now you would like to know, or typically you would like to analyze that how fast is it decreasing. This H is actually a vector, so it has various components, H1, H2, H3. So all of them are supposed to be decreasing, when coming to the true value. First of all, are they coming to the true value? What is the true value? True value is the optimal value which you would have got. Suppose R is not changing. Then we know that if we had calculated the Wiener filtering solution, we would have got the best possible MMSE. No better is possible. So now if we start from some arbitrary initial guess, say H0, and if we apply this adaptation law, do we come to that optimal weight? If we come to that, then it is good in a sense. It is at least approaching the best. So does that happen? And if it happens, how fast does it happen, and when does it happen? So to analyze that, let us assume that this is an error I have defined. So this is the optimal weight H0. So this is my error in estimation at any time n. Right? This is my estimate according to this law, and this is the best possible. So this is the error. Now what will happen? Similarly, if I now calculate Cn plus 1, which is nothing but Hn plus 1 minus H0, that is, I had this much of error at instant n. Now according to the update law, if I calculate Hn plus 1, I will have this much of error at n plus 1. Has the error decreased? That is the question that we are asking. And eventually, at least given enough time, will the error go to 0? This is the question that we are asking. Okay. So for doing that, basically you have to set up a recursive kind of difference equation, xk plus 1 equal to something into xk, that sort of an equation, and then see whether it is stable, it goes to 0 or not. So you have to do that. So that's why I am trying to relate. Now you can easily find out that Cn plus 1 can be written like this. Why? You put minus H0 here, put minus H0 here. So this is Cn plus 1, this is Cn, and here this is okay. So then how do you get 1 minus mu r Cn? So you get here, see this time you have got Cn plus 1, I into Cn is Cn, that also you have got. So how does this become mu r Cn? Because what is H0? H0 is R inverse D, that is the optimal estimate, optimal Wiener filter estimate. So H0 is equal to R inverse D, that we already know. So what is now what is RCN? It is equal to RHN minus R inverse D, which is D. So now if you do what is this? This is D. So what is this? This is nothing but minus RCN. Correct? RCN is RHN minus D. This is D minus RHN. So it is minus RCN. So it is Cn into I minus mu RCN. Correct? It's simple. But what we have done is now we have set up an error equation. Now if we are now only talking in terms of errors. So if the error was here at the nth step, at the n plus 1th step, it will be related like by this. Now whether the error will go to 0 or not will totally depend on the property of this matrix. Right? So the easiest way to analyze it is, as we know, by doing what is known as an eigen decomposition. Then this matrix will actually become decoupled. That is we should see it in a plane which is called the principal axis, where the fall of each error is actually independent of the fall of the other. So we'll get basically we'll get a set of scalar equations. So we know that if we can easily achieve it if we break up, that is the set up a coordinate along the eigenvectors. So we write that R is equal to this, where this is the eigenvector matrix and this is the diagonal matrix consisting of eigenvalues. Remember, we had done this before. and then define a new set of error coordinates. Now previous error coordinates were C, so now I am trying to define a new error which is V, which is defined as Q transpose C. What is the advantage? Advantage is that if you just take it through this, that is if you define this, then now you just blindly substitute. So Cn plus 1 is equal to I minus, this is R. So you have first substituted this, then try to, rather than trying to write in terms of Cn plus 1, let us see how this changes. So Vn plus 1 is nothing but Q transpose Cn plus 1. So you multiply this by Q transpose. This equation multiply by Q transpose here. So you get Q transpose here. Mu is a scalar. So Q transpose Q is actually I. That also we have proved that the eigenvector, unitary eigenvector matrix is its transpose is its inverse, if you recall. So if you multiply this by Q transpose Q, this will go to I. There is a gamma here and then Q transpose C. So you have Q transpose C here, which is Vn, and here also you have Q transpose C, which is Vn. So you basically get this one. What is the advantage? Why did we do this? Because this matrix is now diagonal. This matrix is also diagonal. So this whole matrix is diagonal, which means that now each coefficient of V is changing by itself. It is not affected by any other coefficient. See that does not happen here. This is a non-diagonal matrix. So then Cn plus 1 will actually be related to C1, C2, C3, many C's at n. Say Cn plus, say the first component of Cn plus 1. It will depend on 3-4 components of Cn, because this matrix is non-diagonal. But now by making it on this basis, we have reduced it to a diagonal form, and now I can say that each one of them are basically diagonal. So then we have a set of scalar equations for each component of V. We have a set of scalar equation which involves only that component of V, nothing else. So that K is now restricted, which means that we can simply say that if Vkn plus 1 is equal to 1 minus mu lambda k of Vkn, then when does Vkn go to, when does this go to 0? When this factor is less than 1. Either that is the magnitude of that factor must be less than 1. Then I mean every time you are going to multiply by another less than 1 and then it will finally go to 0. Right? So Vk converges if this is the condition. And if the whole of V has to converge, then each Vk must converge. Now if each Vk must converge, then how should you choose mu? You see, you have chosen mu. Mu is a single quantity, it does not depend on K. It is the same for each K. So therefore you should choose this mu such that you should choose the mu corresponding to the maximum eigenvalue of lambda. If it satisfied it for the maximum eigenvalue, it will obviously satisfy it for all other eigenvalues. Right? So then this is the condition, that mu must lie between 0 and 2 by lambda max. So if this condition is satisfied, then this iteration scheme, given enough time, will converge to the optimal weight. Right? So this is our result. So that's how you should choose the adaptation gain. If you choose the adaptation gain too much, then the process will become unstable. Right? Just like control. Even in control, if you increase your controller gain too much, the process becomes unstable. So this is our, and now we can calculate all sorts of things. So Hi, that is the ith component of my weight, will now converge like this. Now we can write everything because they are now all scalar equations. So you see that as n will increase, this whole term will actually go to 0, which means that this whole sum will eventually go to 0 and this will tend to this. So each component of the weight will actually tend to the corresponding optimal Wiener filtering weight. So this algorithm is okay, it at least does the job. I mean, hopefully given enough time it will do the job. But there are several catches. For example, how do you know R? That is the one of the basic catches. That how do you know R? Actually, what you do is you also try to continuously, and then I mean R may change as you have said. So you have to also continuously update R. It is continuously obtain the latest estimate of R, because you have to, if you want to update, then you need R. Na? This is your update. So you need D and you need R. Now you are asking that if I have D and if I have R, why don't I compute the optimal Wiener filtering weight? Why not? That is usually because of two reasons. If we when we study control, actually everything depends on computation speed. If you ask a chemical engineer, he has when computation is not in his mind at all, because his sampling time in his processes, his sampling times will be in minutes. He doesn't care what amount of time is needed. If you ask an electrical engineer who wants to drive a motor, he will be somewhat concerned, but not too much, because his sampling times are in milliseconds. If you ask a communication engineer, he is extremely concerned about computing time. For example, I think I was speaking with his supervisor. All his PhD work will be on how to compute faster, all these algorithms. So in signal processing for communication, computation is a big issue, because you are sampling at gigahertz frequency, right? Megabits per second, gigabits per second kind of things, telephony. So you can imagine that inverting big matrices every time is a big problem. You can't do that computation every time. So that way the steepest descent algorithm is, the computation is very simple. Just one multiplication and one subtraction. You don't have to solve equations, which you have to do if you want to solve the optimal Wiener filtering solution at every step, right? So, and later on we'll see, in fact the next algorithm that we'll see that how this computation itself is. Now you still have to compute R. Remember that the computation is not only this, computation is this provided you know R and D. But if you want to simultaneously update R and D, then how do you update R and D? There is, the standard, absolutely simplistic way of doing R and D will be this: calculate U transpose U for the last n samples and see where it is. Just simply take an average. That will give you R and D. And similarly, they will give you R, and you can similarly do UN minus Y, YN minus Y to get D. So this is a very computation intensive thing if you want to do it every time. Every time if you have to take n number of samples and multiply two matrices and then add them, that's not a very simple task. It involves computation. So we still have to see that how we can simplify this if we actually want to implement. And actually it is this motivation that gives rise to the next algorithm, which is the LMS algorithm. So in the LMS algorithm, what we are trying to do is we are still doing gradient algorithm. Only thing is that we want to simplify. It's just based on computation. Just based on computational advantage. That if we see that how much of, we want to adapt R, because we know that from time to time R and D will change. That's the basic reason for choosing to adapt a filter. So we know that R and D may change. So we need to adapt R and D, but at the same time we are also looking for simple schemes of computation for R and D. So how do we do that? What is the most simple way of choosing R and D? The most simple way is to simply reduce this n to 1. That is, don't take averages. Average means every time so many computations will come. Just take 1. See, without taking 1 you can't compute R. So that's the best that you can do. That's the least that you can do. That at least just take for that sample and then assume that is the R. Obviously it will not be the R. It will be 1 outcome of a stochastic experiment. After all, u is the outcome of one experiment. So if you are, why actually you should take ensemble average. If you want to compute R, actually you should take ensemble average. You are not doing that. You are assuming ergodicity and you are doing a time average and thinking that if you take n long enough, then the time average will be very close to the ensemble average, because you can't do ensemble average in real time anyway. You can, people are, computers are beginning to become faster and faster. People are now thinking of doing real time, Monte Carlo kind of algorithms where they will calculate ensemble averages in real time. Those algorithms are now being proposed because the computational platforms are becoming very, very fast compared to the application demand times. So in some applications such algorithms are also coming, but definitely not in communication. Communication itself is so fast, you are trying to, no question of doing ensemble average. So you are doing time average. Now time average, we have seen that if we take a random variable and if we try to, suppose it has a mean, right? We take a random variable, okay, several random variables. So if we take, this comes from a distribution which has a mean. We don't know what is the mean. Okay, all we know now, still we want to estimate the mean. This happens in so many times. So what is it that we do? We simply take n of them and then take average, and we assume that that is the mean. Now that is not the mean. That is another random variable which has been computed out of these. So that itself has a mean. This mean estimate itself is a random variable which has a mean, and that mean converges to mu. True. That is, if you take expectation of this, you will also get mu. But so then, what's the big deal? I mean, from one random variable we have got another random variable. Is it any better? It is better, because the variance of this random variable is going to be much smaller than the variance of these. So now every time you do it, you are going to get something which is very close to mu, because the variance of this is low. That is the advantage. That is why you do averaging. So here also you are doing the same thing. If you do averaging, then this quantity will still may not give you R, but because you have done an n-point average, it will give you something which is close to R, because the variance is decreasing. Now if you now want to reduce n, that is, reduce the number of terms with which you want to average, then what will happen? Mean will still remain the same. That is, the expectation of this will still be R, but the variance of this estimate will now increase as you reduce n. You have to pay a price somewhere. So that's why that is the price precisely which you pay. If you compute this thing based on only one point, then your estimator variance will increase. And from sample to sample, even if R remains constant, from sample to sample, this Rn will widely vary, right? And this Rn drives your estimate, because that's there in your algorithm. So if you have flickerings in this R, you are going to have flickerings in this. That's the price you pay in the LMS algorithm for computational simplicity, right? So what happens is, what you do in, even fully knowing this, you want to do it sometimes, So there what we say is that we estimate R like this. You see, I have not taken average, simply one term, only un u transpose n, and then dn is this, simply u and yn, again one term. Turns out that obviously expectation of R hat n is R, because if you take expectation here, they will converge. This will be R. So the mean value will remain as R and D. That is true. So even if they will flicker, their mean will be the R and D which you should have, used if you wanted to get an ideal steepest descent. But well, you are sacrificing that. So now your performance criterion is this. It's simple. just if you that is in place of this you put this, and in place of this you put this. These are your estimates that you are substituting, and then you simply, so now this is your rule. If you just put this plus mu minus mu this Jn, if you put, you will get this form. So now you see what is the what are you doing? Look at this, that you are updating. What is your, which is the error that you are updating on the based on the current value of error, just on the current value of error. So all your estimates, so your update is in this direction, and it is based on the current value of the error, because this is what, this is nothing but y hat n. All right, and obviously now if you, what are the goodness of this? At least if you take expectation on both sides, this will be expectation, and here if you take some mild conditions, if you assume that things are uncorrelated and you can put the expectation inside and all, some mild condition, it turns out that these will then converge to their corresponding counterparts, and this estimate, that is the LMS estimate, expected value of LMS estimate will converge to the corresponding steepest descent algorithm. That is, I mean actually speaking, practically if you find that these are the optimal weights, and you have started your say this is the H0 H1 space. Suppose there are only two coefficients that we want to adapt. So maybe that the LMS algorithm will go in this path, then the steepest descent algorithm, if we use the true value of R and D, while if you do an LMS algorithm it will go like this. So in the expectation it will still follow the steepest descent path, but on its journey it will oscillate because the variance is high, right? But still this is not all that bad, because still it is roughly going to follow the basic steepest descent algorithm, which we have seen that if we define our adaptation weights carefully, which will come fairly close to the optimal weight. So at least we can expect some performance. But there is a basic problem of all gradient algorithms. All gradient algorithms, including numerical optimization, numerical solution algorithms, have this problem, that the gradient algorithms have very slow convergence near the minimum. So they will, suppose you are here and here is the minimum, initially they will come very close fast, but then towards the end they will become slow, because the magnitude of the gradient itself will become smaller, because in the optimum del j, that is del j del h is equal to 0. That is how it is a minimum. Now your updatings are also based on this del j del h. So as it comes close to the minimum, this amplitude will become smaller. So every time as you are approaching the minimum, you are becoming slower and slower. That's the biggest problem of all gradient algorithms, including this steepest descent and LMS. So that's their problem. And if you want to, there are other algorithms which will accelerate convergence. Let us not look at this. I just sort of wrote it for completeness' sake, that there are other methods of accelerating convergence. That is by using Newton's algorithm. That is, you don't take only first order terms. Gradient algorithm assumes that the performance surface can be approximated as planes. So at any point it will assume that it can be approximated by a plane. That plane will go on changing, but it will intrinsically assume that the surface is a plane. Now you can improve that, and you can assume that the surface is a parabola. So you can consider the second order differentials in your Taylor series expansion. If you define an estimator based on that, then you get what is known as Newton's algorithm, which has much faster convergence, but which has much higher computation. So everywhere, I mean, you cannot eat the cake, and generally you cannot eat the cake and have it too. So if you want faster convergence, you have to spend more money and buy faster computers which will do faster computation. So without paying that money you cannot get away generally. So these are the two major points. Firstly, that the gradient algorithms have slow convergence near the minimum, and the second is that the LMS algorithm estimates are generally noisy due to this single point estimation of R and D. Okay, so that's where we end. So what did we see today? Just to recapitulate, what we have seen is that we have first seen optimal estimates in the Wiener filtering sense. Now we are seeing schemes where if we start from an initial guess and without ever solving the Wiener filter normal equation, we are just adapting the estimate, right? And we are saying that this will be useful if first of all because of less computation, and the second because these R and D parameters make constantly change. So it's not possible to constantly every time evaluate R and D and try to solve the optimal equations. That's not easy to do when you have to do it very fast. So we are finding out computationally efficient adapting structures where the weights are very simply adapted, and if you give them little time, then they will come very close to the optimal estimates. Even otherwise they will constantly be tracking the optimal estimates. So we have seen two algorithms, steepest descent and LMS, which are basically gradient based, and seen some desirable properties. So we are ending our discussions on what is known as adaptive filtering and linear optimal filtering here. After the exams, we have the major topic is Kalman filtering, which is state estimation. Wiener filtering is just in a sense it is input output, that is based on some measurements you want to explain other measurements. But Kalman filtering is estimation of state, and then we will have to do something on system identification, that is all this time we are talking about signals. Sometimes we have to estimate coefficients in systems. So what is the resistance of a motor as it is changing, or what is the inductance, like that, or what is some friction coefficient. So how to do that? So that is our plan. So that's all here today.